Yes, derivation of bus admittance matrix by singular transformation method. The derivation begins like one of the method we have seen Y bus by insection method. Rule of insection was seen in the earlier interaction. So here this is another method of obtaining system admittance bus. The power system, however complex, is that its representation in terms of admittance notation as a matrix, as a Y bus of a system can be done, which is useful to perform load flow study, short circuit study, stability, other associated analysis. What one would do, it become a base for that. Then in that requirement, the another method to obtain Y bus is Y bus by singular transformation method. That begins in this way. So as we have, you can see at the right side corner, I have put a equation I plus j equal to y into v. What is exactly this? It should be I bar plus j bar equal to y matrix into v bar. This is one of the representation we got when we represented generalized network element, generalized primitive element in admittance form. A vector of branch current I, a vector of equivalent current sources in the branch got connected as a J equal to primitive admittance matrix of the system into the voltages of the bus. So this was what we have seen in the earlier interaction. So vector of I plus vector of j equal to y primitive into v was the one derivation we have interacted earlier in the classes, which was primitive element, primitive admittance matrix. Primitive element represented in admittance form was landed with this equation. Vector of I plus vector of j equal to y primitive into v, where we have understood y is a matrix where elements are diagonally placed. If there is no mutual coupling, if there exists a mutual coupling, some of the off diagonals were non-zero was the recall I would like to bring your attention. In that way, we have stopped there. I plus j equal to y into v in the form of vectorial representation. I matrix, a vector, j matrix, a vector, y being a matrix of element by element or row by column representation and a voltages of v. Now, from this equation, let us take an operation, multiply all the terms by a matrix which is A transpose. How do I take this now? Imagine you have been given a system. A power system layout is given with you. You are able to draw its graph. You are able to write its impedance to all the elements with all the buses, and you are able to take out reduced impedance matrix. I mean to say, A matrix of that system you are able to obtain. Once you obtain A matrix, getting a transpose of that A matrix is just shifting rows to columns and columns to rows. So the work begins. From the admittance form of representation of general primitive element, take that equation, multiply all the terms by A transpose of that system. I don't know how many ones are there, how many minus ones are there, how many zeros are there in the matrix A. It is the mathematical begin of it. If I operate the standard equation I bar plus j bar equal to y into v bar by a multiplier A transpose, I will get A transpose into I vector plus A transpose into j vector equal to A transpose into primitive admittance matrix Y into V. So when I have this equation, look at the arrow I have mentioned. It was seen that from the earlier discussion, when we wanted to look for A matrix, obtain reduced impedance matrix or impedance matrix, you recall back the first term A transpose I was 0 there. It means to say the current KCL applied to each branch or each element over there at a particular junction, the current incoming, current outgoing were reconnected and said 0. It means the first term A transpose I, nothing but sum of all the current meeting at that particular node goes 0. So A transpose I, the first element goes 0 here. What about the A transpose J? A transpose J is the equivalent current source got converted from that branch at the entrance of that particular element. Like K, JSK was the independent current source we obtained, and after having transformed it, it becomes GK in that context. In that way, A transpose J becomes the bus current. So, from this expression, A transpose I that goes 0 because of application of KCL at that branch, and A transpose J will not go 0, and that represented as I bus or bus current at that element equal to A transpose Y into V. This will be a standing point. When I use that knowledge and I have another concept, the branch voltages V1, V2, V3, V4, V5 around that particular representation from the nodal voltages. In my representation on the board, I referred E1, E2, E3 as bus voltages, V1, V2, V3, V7, etc. as elemental voltages, branch voltages. Now, same equation, how KCL and KVL can be viewed on incidence matrix was the conclusion when we were interacting with respect to incidence matrices. So, I have taken the branch voltages, vector of branch voltages equal to A matrix of that system product with bus voltages like V1, V2, V3. Those many buses are there in the given power system. The nodal voltages like V1, V2, V3, V4, capital V1, V2, V3, V4 like that. If I operate them, I'll be able to get individual vector of V1, V2, V3 branch voltages. So this equation was shown as an extension of A matrix approach. So that is recalled back here. Then the second term, A transpose J won't go 0 when I apply KCL to the particular element. Then that is represented as I bus. Then we know from Ohm's law representation, Ohm's law in admittance form, I equal to admittance into voltage, I equal to Y into V, like I equal to V by Z, how we write in terms of impedance form of this. The same thing is written in admittance form as I equal to Y into V, where Y is 1 by Z, like that. So from this, if I use the subscripts of that representation, I to I bus, Y to Y bus, and V to V bus, you can see that equation followed by that. Then using those above standing equations, where I bus is a representation of A transpose J, which won't be 0. V equal to the branch voltages of the total network in terms of nodal voltages, A into V bus. If I use them in this representation, I can get I bus equal to A transpose Y into V. Then again I will get this representation substituting the respective equations over there. I bus equal to A transpose Y, where V is replaced, small v, the voltages of each element in that system. However, V1, V2, V3, lowercase v1, V2, V3, V4, V6, etc. from bus voltage relationship by A matrix, which is going to get transformed as I bus equal to A transpose primitive matrix Y into A and V bus. Now you have to look into this case. At the left side I have I bus, at the right side I have V bus. So V bus, if I take on a LHS side, I bus divided by V bus, I by V concept. I by V concept works out Y bus. That you can check by equation 2.9 on the screen, where I bus equal to Y bus into V bus. Retain Y bus there itself. V you transfer to the LHS side at the denominator. So I divided by V give you admittance. In this equation, where I bus equal to A transpose primitive element matrix into A into V bus, if I take at the denominator of the LHS side, I'll be getting Y bus equal to A transpose into primitive elemental matrix into A. This is called as transformation of the primitive elemental admittances, parameters and variables into meaningful representation as Y bus. Exactly what we have done. Mathematically, we have moved forward here. What has exactly happened? This Y bus by singular transformation method is transforming the variable, the unknown things in the system, and parameters of the network singularly, because matrix A is not a square matrix. It is going to transform it into Y bus, which is meaningful. Hence, transformation we call as singular transformation of elemental data Y and parameters into a meaningful data Y bus. Hence, the transformation what has been taken over here is by the use of matrix A, which is singular. So, singular means you must be knowing the determinant we cannot define. Therefore, it is nothing but A matrix is singular over here. So, A matrix nothing but one of the column got eliminated from the all incidence matrix that is serving as a base for us. So, that is singular. Hence, the transformation of elemental admittances and variables into a meaningful bus identity for the further calculation in the power system. This method we call as singular transformation method of Y bus. So therefore, at the LHS side, I have a Y bus, and at RHS side, I have a particular power system, A matrix and A transpose of which, and primitive admittance matrix of which. If I have been given a problem of a given electrical network, if I have said to obtain Y bus of that given problem, then I will be using this equation. What is that? Y bus equal to A transpose into Y into A, where A stands as a reduced impedance matrix of that given problem. Then you might ask me, how to obtain A from A cap? You must be given an instruction, which is a reference bus in that given problem. That reference bus related data you need to delete from that information. Then that serves as A matrix for you. Then you have to take A transpose of that, keeping ready. A transpose. How about Y? Y is called as primitive admittance matrix of the problem. This is a matrix of what dimension? How many elements are there in the system? If there are 100 elements, it becomes 100 cross 100 matrix. Therefore, the elements will be placed only on the principal diagonal if there exists no mutual coupling. If there exists a coupling, definitely Y bus will not be having zeros at the upper triangle and lower triangle of the matrix. Some of the elements are non-zero. So let us apply this concept, which is very simple, straightforward one derivation. Obtain, derive Y bus by singular transformation method would be a mathematical demand. At that time, as I begin, we know from Y bus by admittance, primitive elements in admittance form of notation, we have I plus j equal to Y into V. From that line, you have to begin and you have to use this concept and land with the equation Y bus equal to A transpose into Y into A. That's what the plain derivation worth 5 to 6 marks a question at all. Then when it is applied to a numerical problem, how it works like. Now look into a problem. The particular power system, I wanted to highlight you. A Y primitive matrix would look like this. Elements are diagonally placed. I have randomly taken a problem. I will tell you what is the problem I have taken. There are 7 elements. Elemental admittance is represented only on the principal diagonal, where Y11 refers to element number 1 admittance. Y22 refers to element number 2's admittance, so-called Y77. And upper half of the triangle, you can just see here, the triangle, here it is empty. This triangle is empty, means 0. And lower triangle is also empty. It means there is no mutual coupling between any element. This is Y primitive. Now I will focus, which is the problem I have taken. You recall that the problem which I have taken was the one which we have discussed. This is the problem. I go back to the first diagram. This is the problem. This is the electrical power system layout whose Y bus I want to obtain by singular transformation method. Then for this electrical network, I should check how many buses are there. Physically, if I count 1, 2, 3, 4 and ground is hidden here. So there are physically 5, but practically you will find 4 on the representation. Ground is a hidden reference. Then it is represented at the bottom of the presentation, 0 as a reference, 1, 2, 3, 4 as distinct buses. Connectivity among them is established by line segment. Each line segment represents connectivity of an electrical element between nodes or buses. and orientation has been given to the individual element. You might ask me, do I need to do the element orientation or it will be given? If it is given, we should refer. If it is not given, we shall attribute a direction to that and we have to follow the direction which we have assigned. So therefore, let us consider this problem which we have already visualized. There are 4 buses excluding reference bus, 1, 2, 3, 4, and we have 7 elements. Then incidence of all the elements with all the nodes I should calculate. So for that, this slide would be helpful to you. So this bus will give you, there are 4 columns vertically if you can see. Column number 1, column number 2, column number 3, column number 4. So this problem I have modified for today's need. So matrix A refers to reduced incidence matrix. Number of rows you will find 7. Number of columns you will find 4. It means 7 cross 4 is the dimension of matrix A. Where is the 0? 0 is personally deleted. I have removed the column pertaining to reference bus. The first column itself is bus number 1. You can visualize, when I visualize bus number 1, how many elements are interconnected to that bus number 1? Incident, Aij rule. Element number 1 is inward. You can see first row, first column, element is -1 because it's inward. And element number 6 you can check, 1, 2, 3, 4, 5, 6. Because there are 7 elements, minus the 1. 1 down, I have 6th row. Under the first column is +1. It is Aij is +1 if it is directed outward. So hence I have done. The first column refers to bus number 1. You can visualize. Second column refers to bus number 2. Third column refers to bus number 3. Fourth column refers to bus number 4. You can visualize. If I witness you at bus number 4, look to the last column. How many elements are interconnected to bus number 4? Element number 3 is inward. It must be -1. You can check. Row number 3, column number 4, it is -1. And element number 4 is outward. It must be plus. You can check. Row number 4, column number 4, +1. And element number 7 is inward. It should be minus for you. 7th row, 4th column. You can see -1. So it follows the same rule, Aij rule. So direct formation of bus incidence matrix or reduced incidence matrix wherein the column or a row which is pertaining to a reference bus is deleted. Now you have witnessed me. This is the problem I have taken. Now I assume all the elements possess admittance. Elemental admittance of element number 1 in this diagram is Y11. Element 6 possess Y66. Element 5 possess Y55. Like that, each element is possessing elemental admittance. They are the one which I am going to use in Y primitive matrix. So, A matrix of the problem must be formed. A transpose is quite easy. Change the rows to column and alter it. It becomes A transpose. Now, getting Y primitive matrix of this problem, I should check how many elements are there in the system. Of course, in this problem, as you can visualize, there are 7 elements. Then elemental matrix will be 7 cross 7. Then I will be having the particular matrix. I will go forward. So this is the problem I am using. I come to the point where I am. Can you see now? Y primitive matrix in the equation 2.13 is placed with 7 values diagonally. Y11 refers to element 1. It is called 1 cross 1 element. Y22 is 2 cross 2. Second row, second column incident. Like that, diagonally you will find all the elements incident to representation. Then when I have A matrix ready with me, A transpose I can get, and Y primitive ready with me, look at the representation. Therefore, Y bus of the given problem is A transpose Y primitive into A. I wrote the equation there. Now you check the representation. I have substituted or placed A transpose matrix at the start point. Then I place Y primitive matrix, which is diagonally placed into A matrix. Now we can see A transpose, just transpose of each other. Yes, they are. Now A transpose into Y primitive into A. I have to reduce this mathematically. As you have product of matrices, number of rows, number of columns, with their rule, if you could check, I can reduce it. So Y primitive is 7 cross 7 and A matrix at the right side, extreme right side is 7 cross 4. I can multiply. It is nothing but first row, first column. Second row, second column. Third row, third column. If I multiply, I can simplify product of two matrices, Y primitive and the last matrix A. Get the immediate answer. Take the product of that with the leftmost matrix, which is A transpose. Then I will be having the total matrix dimension. The first matrix A transpose is having 4 cross 7. Central matrix is having 7 cross 7. The last matrix is having 7 cross 4. If I operate this entire matrix by product, the final matrix what I get, which is Y bus, will be having a dimension, the rows of the first matrix and a column of the last matrix. Nothing but 4 cross 4 will be the answer matrix what I am going to get. So, central matrix, which is a primitive element, 7 cross 7, take a mathematical product with the extreme right, result a tentative answer, take a product of that with the A transpose and leave the answer, which is 4 cross 4, which is nothing but like this. Can you see this? I have put a matrix here. So, you can just see this. The same thing I have put over here. So, took a product of the central matrix and the last matrix and I kept ready. I just switch back and come to you. Y primitive into A is resolved as a simplified matrix and which is waiting for the final simplification with the A transpose. Now you can see the A transpose is having 4 cross 7 dimension and the immediate tentative answer is having 7 cross 4. When I take a product, it should give me 4 cross 4. You can see the circled number 4 cross 4. So this is how a dimension can be filled. Now, if I have been given elemental admittances 0.1 J mho or 0.25 mho like that, each element was supposed to be given with some numerical admittance, then I would have taken real-time addition or differences of them as shown in the matrix. So Y bus would stand as 4 cross 4 matrix with a Y11 standing with elemental addition of 1 and 6th element. You can see that. What is Y11 for me? Elemental admittance of element number 1. What was Y6? Elemental admittance of 6. You might ask me, why you gave double subscript here? So, it is sufficient if I give single subscript Y1 itself. But it was already a predefined problem in the presentation of the author. I referred directly. So, I modified it as per my requirement. It was some other domain. I just modified it. It means Y11 plus Y66 I would have represented simply as Y1 plus Y6 also. But this author referred this problem in some other study of power system analysis. He could resolve it himself as double subscript. It doesn't matter to me in this case. So, Y11 refers to elemental admittance of element number 1. Y66 refers to elemental admittance of 6th element. Now, you just look carefully on the diagonals of that matrix Y11. Addition of two elemental values. What are these Y11, Y66? These two are the elements interconnected to bus number 1. Look at 2 cross 2. Just by curiosity, look at 2 cross 2. 2 cross 2 is sum of the admittances of the elements interconnected to bus number 2. Now you recall Y22 is there. There must be element number 2 interacting with bus number 2. There is element Y55. There is a numbered element 5 must be interconnected to bus 2. 6 is there. 6 must be interconnected. 7 is there. 7 must be interconnected. It means Y22 is sum of the elemental admittances of all those elements radiating or connected to bus number 2. There are 4 elements. I will go back to the problem and convince you. 2 is there, 5 is there, 6 is there, 7 is there. I just go back and convince you. Can you see here? At bus number 2, 2 is there, 5 is there, 6 is there, 7 is there. There are 4 elements interacting at bus number 2. Hence, at y22, I should get 4 elements, like rule of inspection. You recall that? Similarly, it function over here. Mathematically, you can take sum of the admittance of y22 plus y55 plus y66 plus y77 to get capital Y22 or elemental admittance diagonal, which was shown here. 2, 2, 5, 5, 6, 6, 7, 7. Likewise, you just move curiously with the third bus. Y33 means 3 cross 3. How many elements are interconnected? 2 elements. Element number 4, element number 5 with the admittance Y4, 4 and 5, 5. When I take addition, that results in the grand term 3 cross 3 element of a Y bar. Similarly, go to fourth element, 4 cross 4, diagonally cross. There are 3 elements. You are witness. Element number 3, incoming. Element number 4, outgoing. Element number 7, incoming. There were 3 elements interconnected to bus number 4. So that is witnessed. If you are still curious, just look at the matrix A transpose over there. A transpose matrix give you at the 4th row, how many elements are physically countable? 3. 3 elements are here. Like that you can check into. So at the 3rd row, how many elements are there? Minus 1, minus 1. Physically there are 2. You will find 2 elements over here. And in the row number 2, how many elements are there? Countable? 1, minus 1, 1, minus 1, 1. No, not to take any minus plus. Just count the numbers. 4 physical count. At Y22, you have 4 elements. At Y11, in the row, how many non-zeros are there? Minus 1, 1. 2 are there. 2 elements. So, like A matrix or A transpose would give you how many elements will come in each diagonal can be seen this way. This is about diagonals of the Y bus obtained by singular transformation method. What about the off diagonal? Look into that. Row number 1, column number 2. What is this? Minus 6, 6 and 3, 0, 4, 0. What exactly it indicates? It is the negative of the admittance of the 6th element connected from bus 1 to next bus 2. That's the indication. 1 cross 2, row number 1, column number 2. What is the meaning of that? 1 cross 2. Nothing but there is a physical connectivity from bus 1 to bus 2 by elemental data Y6, whose negative value is present in the Y bus of the representation. Minus of real-time data Y66 should be placed in 1 to 2, 1 cross 2. There is no physical element between 1 and 3, hence it is 0. And there is no element between 1 and 4, 0. Now just move to second row. Second row, what is the first element you find there? 2 cross 1. 2 cross 1 refers to minus Y6, 6. It is same as 1 cross 2. Can you visualize that? You mirror this matrix along the diagonal. Along the diagonal, you mirror and check. 1, 2 is same as 2, 1. 1, 3 is same as 3, 1. 1 cross 4 is same as 4 cross 1. And similarly, 3 cross 2, 2 cross 3. 4 cross 3, 3 cross 4. You can visualize. So there is a mirror. Means similar number reflects from an upper triangle to lower triangle. So this was seen in Y bus by inspection method. So I come back. Second row, first column. Y21 refers to negative of the admittance lie between 1 and 2. Nothing but 6, 6 is the admittance and negative of it is placed. Yes, there is. Negative of the admittance between 2 and 3 is minus Y55. And is there any element between 2 and 4? It is there. Element number 7 itself is an indicator that there is an element between 2 and 4 whose negative minus of elemental data is represented. So you could complete row number 2. Slowly you move to row number 3. Y31, 1, 3, 0. Y32, same as 2, 3. There is a minus Y55, the same thing appear here also. Then diagonal element is sum of the admittances of the elements connected at bus number 3. And how about 3 to 4? Is there any element between bus 3 to bus 4? There is an element between bus 3 and bus 4 by elemental data Y44, and negative of that is placed. And once you complete that, look at the 4th row, automatically ready. 4, 1 is 0 because of 1, 4. 4, 2 is ready because of 2, 4. 4, 3 is ready because of 3, 4. And 4, 4 is sum of the elements. But here you must observe very carefully. The main diagonals are with a plus. Y11, 166, like that. Observe the off diagonal. If there is an element, it is with a minus. If there is no element, it is 0. So this is a speciality. The diagonals are with a plus and off diagonals are with a negative of the elemental admittance of the system connection. This you have to observe and remember. And if it is physically seen by a numerical problem, we can see how numerically a problem can be worked out if you have been given elemental data. So by this I get back how we were I plus j y into v. We took a y bus by A transpose y primitive into A, whose realization by what is primitive matrix, what is A matrix, what is A transpose for a sample problem. When I take a product of them, I was tentatively with the intermediate answer and concluding answer. If I have been given real-time values of elemental admittances, I would have really counted the values. Now here I would like to state, what is the output matrix Y bus dimension? It is 4 cross 4. Looking to the problem, how many buses were there in the real problem? There were really 4 visible buses, 1 ground was invisible. It means practically you had 5 buses, but output matrix is having 1 minus. It means to say the difference between Y bus by inspection method, Y bus by singular transformation method is the size of the Y bus is 1 lesser to the total number of buses in the system. If there were 5 buses, 1 will take off and 4 cross 4. If there were 100 buses in the power system, which is a reference, one of the number, you delete that. So 99 cross 99 will be your Y bus. The same problem, if I work by Y bus by inspection method, what would be the dimension of the Y bus? 100 cross 100 at that time. It will include reference. There is no meaning of reference bus in Y bus by inspection method. Hence, n cross n is the dimension of the Y bus in inspection method. Y bus by singular transformation method takes, it is n minus 1 cross n minus 1. Why the minus 1? The minus 1 is because of taking off the reference bus from the context. Therefore, this is the difference between Y bus by inspection method, Y bus by singular transformation method. So I will move to the next parameter. So this was presented once again here, and you have been given problem. So what are the diagonals? What are the off diagonals? You can just see whatever the discussion I have done, the similar thing is present over. It witnesses you. So what is Y11? 2 elements are there. What is Y22? 4 elements. You can just witness this graph and matrix there. So the zeros are no connectivity, it indicates. But you should remember, minus comes in the off diagonal. Okay? Now, the similar one. Suppose one of the element is deleted there. You can see that. Suppose there is a modification done. It is out of our scope, but still then I would like to. You can see there, element number 2 to 3, bus number 2, 3, one of the element is missing there. So in this way, how modification takes place, that correction has to go. We will not work about this. Okay. Now I will take a problem. Look at the numerical problem. Okay. The same problem. You have elemental impedances, not the admittances. There are so many buses. Elements are mentioned. J.6 ohm, J.4 ohm, J.5 ohm respectively. And impedances of the elements 3 to 4, 2 to 3, 1 to 2. Will not worry. All the elements are given with the data. That's the meaning. And look at the speciality. The mutual impedance between the elements 2, 3, 2, 4. What do you mean by elements between 2, 3? Bus 2 to 3, there must be a connectivity. Yes, in the diagram, there is a transmission section from bus 2 to bus 3. And 2 to 4, there must be a transmission line between 2 and 4th bus. Yes, there is a transmission line. And he explained there is a mutual impedance between, mutual coupling is there. Earlier to this problem, what we have discussed, no mutual coupling. Y bus, Y primitive was your only matrix with the diagonals present, off diagonals were perfectly 0. So only elements are placed on the principal diagonal. But here, this problem poses you a difficulty. It is not that all the elements are plain enough. They may have mutual coupling between any of the next elements. In that context, this problem gives you an insight. There is an element, bus number 2 to 3, having some impedance. There is an element 2 to 4, having some impedance, have coupling between these among themselves by j.1 ohm. And if it is given, obtain Y bus of this system using ground as a reference. There is an instruction. The ground is marked as 0 as reference. So no matter, I just turn the next page, you will see how it is represented. You can see. This was the same problem. It looks like the same problem where you will find numerical data. In the place of y11, you have 0.6j. In the place of y66, you have j.2. And you have all the elements given you numerical impedance. You must be careful. The first problem what I dealt was directly admittance. It was y11, y22, y33, y77, etc. I have referred it directly admittance form. Hence, I was very easy to go A transpose into Y primitive into A, yielding me Y bus. It was a straightforward work for me, provided I have the data in admittance form. But this problem is posing you, data is not in admittance, data is in impedance form. If all the data is represented in impedance, it is my first task to convert impedance to admittance. Hence, look at the representation. All the elemental representations were put with a numerical content. And you observe one flower bracket over there, element between 2 and 3, element between 2 and 4, were coupled mutually by j.1. This is the representation. The problem is an abstract here. So this problem, whatever is the mentioned content, is drawn as a conclusion on this diagram. Graphically it is represented. You might ask me, how could you draw sir these arrows if the arrows are not mentioned in the problem? So I was given you an instruction. If arrows were given, you would have taken. If arrows were not given, you can mark and adhere to those directions till the completion of your mark. Where do these arrows are useful to you? These are useful to you to frame a matrix of that system. If it is the incoming, you have taken minus. If by mistake your friend has marked outgoing, they will take +1. No matter A and A transpose of the same matrix you are using in the product, that will nullify your work. So therefore, it doesn't matter whether you take an upward arrow or a downward arrow for a system, but you have to be confined till the end of the problem. Whatever you have taken should be maintained. In that regard, this problem I have picked because already it has been seen without mutual coupling by y11, y22, y77 in arbitrary manner. But now you have been given z11, z22, z33, z77 in the form of impedance. And between elements 2 to 3, which is a bus 2 to 3, a j.2 ohm, and between 2 to 4, j.5 ohm transmission lines are mutually coupled by a mutual impedance of j.1. You have to understand from this. So that information is put in the matrix. You can look into primitive impedance matrix. So even I have not discussed this primitive impedance matrix. It has come to your observation. What is a primitive impedance matrix? It is a matrix of element cross element having its elemental impedance put on the main diagonal, and rest of the values are 0 if there is no mutual coupling, and there will be non-zero if there is a coupling. The same definition like admittance, wherever keyword admittance I pronounce, I should use now impedance. Like that, you can see Z matrix equal to J is taken outside the matrix because everywhere J is there, J is taken out. What is 1 cross 1? Elemental impedance, element number 1, Z11. What is Z22 for you? It is 0.4. Look into 2, element number 2, connected between ground and 2, J.4. It is put diagonally 2. What is element number 3? Which is 0.5, 0.25, 0.2, 0.2, 0.5. Look only diagonal. Diagonal are the self impedances of each element of this system. You can go sequentially. 1 means element number 1. 7 means element number 7. What is the 7th value? J 0.5. You can see that J is taken outside, 0.5 is written in the matrix. So therefore, all the diagonals represent elemental impedance. Now, what is the specialty of this matrix? Look at the row number 5. 5 cross 7. We just go along the row and see there is a number 0.1. And 7 cross 5. 5 cross 7 and 7 cross 5. Observe these two. There is a non-zero element 0.1, 0.1. Remaining empty spaces are zeros only. What it indicates? There is an element in the system between 2 and 3. What is the number of that element? 5. Fifth element is between bus 2 and 3. What is the element number 7? It is the element between bus 2 and 4. It would mean element number 5 is mutually coupled with the element number 7. Other way, element number 7 is mutually coupled to the element number 5. It means its mutual coupling should be reflected in the matrix at 5 cross 7 and 7 cross 5. Element numbers, what you find, that element forward and reverse, you have to mention. So, element 5 is coupled with the 7 by 0.1 as well as element 7 coupled with the 5 by 0.1. This coupling is bidirectional. In that context, you look to the 5 cross 7, row number 5, nothing but element number 5. Go along the horizontal axis till the 7th column. It is connected to 7th element mutually by 0.1. The same way when I come to 7th row, go horizontal up to 5th column. You will find same number 0.1 coupled mutually to 0.5. What is the meaning of this? If there exists a mutual coupling between any two elements, at least two elements are non-zero in the matrix. Otherwise, if there was no mutual coupling, the empty space was seen as zeros only. But there is a presence of 0.1 because of element 5 coupled with element number 7. In this way, this is one coupling. There can be any number of lines coupled any number of other lines. Then those many non-zeros are present in this matrix. But all these entire representation in the form of impedance only. Now, what is that required for me? Admittance. Then what I should do? Take the inverse of this matrix. Now, this is a very big task. How do you invert the 7 cross 7 matrix? Very difficult. In the examination, you cannot do it by calci. Calci can do for 3 cross 3 only. Hence, you must be capable of inverting large matrix more than 3 cross 3. But when a numerical problem is posed to you, usually they will see to it that 3 cross 3 become a dimension. Else, it is a task that we should understand how to split this large matrix into small matrices and take partial inversion step by step. That's what is left off. So, once I have an impedance notation, this is the way. You may ask me, suppose entire data is given in admittance form only, and coupling is also given in admittance only. No doubt it becomes YPRI directly. No need to invert at that time. I have been given impedance form of representation, hence it is necessary for me to convert to admittance. If entire data was given in admittance itself, including coupling, no doubt the straight substitution in the matrix position serve as Y primitive for you. You would have used A transpose into Y of that into A of that directly. But we should be very careful in the numerical problem. The data of the problem is given you in the form of impedance or in the form of admittance. Here we are in impedance notation. Inversion of Z to get Y is very necessary. Next, I will move to the next slide. I have got an inversion. You can see there is a difference between the Z matrix, what I got here, whose inversion, if I do, I could do in MATLAB or I could do in some alternative technique, if I get it in this way. You can see it is not element by element inversion. You mind it please. If 0.1, 7 cross 5, 5 cross 7 were not there, individual inversion is possible. 1 by 0.6, 1 by 0.4, 1 by 0.5, so-called diagonal 1 by is possible, provided there is no mutual coupling. If there is a coupling, you cannot do element by element inversion. Personally, you cannot do. It is wrong. Therefore, whole matrix you have to work. You can see it is not 1 by whatever the value. Whatever the value you have here, it is not 1 by. Is it correct? Therefore, it will be checked carefully. It will be wrong if I do personally. Once I keep this Y ready, my next task is A matrix of that. Although we have seen how A matrix of that is obtained. If I know A, if I know Y of that from direct or converted to Y, A transpose into Y primitive into A works for me as Y bus of the system. You can see this. I have substituted A transpose Y primitive into A. When I take a product, it will result me 4 cross 4 only. It's clear. It should result me. So therefore, I should be very careful how I should get this answer 4 cross 4. Because there are 5 buses, of course. 5 buses and we should take into. So this way things work and resolve it into pattern. Okay. Now you can see this answer is not the same answer as we have seen here. This answer, when I obtain the answer for this, you can see this. This is different. So it looks 4 cross 4, but values are directly admittances over here. And there is no coupling at all. You can just go back. All the elements are only on the diagonal. No elements across the upper triangle or lower triangle. Hence it is non-coupled case. But what I am dealing over here is coupled case. There is a mutual coupling between number of elements. Therefore, it should be resolved carefully. 4 cross 4 only, but elements are not same. So, it requires a small work. So, such another example I can take on board in the next class and you can go ahead. So, this is to understand the principle of Y bus by singular transformation method, where it is a transformation of parameters and variables of the system using matrix A by singularity of that. It's called singular transformation of Y bus. So this is how things work. So maybe another problem, if I focus, I can do it. So in the next class, what I would like, I'll take a problem on board. So on board such